Good morning, dear students. Welcome to this session on pre-stressed concrete. We are discussing Unit 2 of your syllabus, where we are majorly talking about the analysis of pre-stress. So, when a beam is pre-stressed by a pre-stressing force, capital P, with an eccentricity, maybe or may not be, maybe axial pre-stressing or eccentric pre-stressing. Uh, the ways that we can find the resultant stresses in the member by different ways, like one is the overlapping of stresses from different sources, like direct pre-stress from bending, and stress from live load, stress from dead load. If you all these stresses are overlap, uh, then you will get the final resultant stress. Similarly, the other concept of now pressure line or thrust line or C line. So by locating thrust line, we are able to find the resultant stresses also, and we will understand very well what is going on inside the concrete when there is a load acting on the member, how it is going to resist. Say if you have some load acting on the member, so what type of resistance mechanism is developed inside the concrete, that is being seen in this C line concept, like thrust line or pressure line concept. Okay, so we have even compared with, RCC to pre-stressed concrete also, where to resist the external load, RCC member is going to increase its loads, the tensile force and compressive force values, having fixed lever arm. Whereas pre-stress concrete is different. It is going to change its lever arm by having constant internal forces, the resisting couple, what you call T and C values, tensile force and compressive force values. So complete opposite mechanism, whatever for the increase of loads, the behavior of load resisting mechanism behavior is completely different when compared to RCC and pre-stress concrete. And the other concept, like load balancing concept, where the choosing of the cable profile depending on the load that is being acting on the concrete member. Say if there is a point load, so we need to have a resisting point load developed inside the concrete. So that is possible by having a kink in the cable profile wherever there is a point load. The sudden change of angle should be there in the cable profile. That is what we call a kink. Okay, so that is if you have UDL, you should have force developed everywhere, because UDL means the uniformly distributed load, distributed. The same resistance also should be distributed. So that's why parabolic cable profile is suitable. Likewise, the load balancing concept is majorly talks about choosing proper cable profile for a particular load acting on the member. Likewise, different concepts we have been talking about, and also we have talked about stresses in tendons. Uh, the pre-stress that you induce is going to change once the pre-stressing operation is over, and once the member is taking the service loads. all this, right? So now we are talking about the cracking moment. The bending moment that is required to provide the visible cracks in the member. Let us see what is meant by a cracking moment and how do you calculate the related parameters with the cracking moments, right? The bending moment at which visible cracks develop in pre-stressed concrete members is known as cracking moment. So, for example, if you have a member, a pre-stressed concrete member, okay, uh, say it is pre-stressed by a cable, something like this. So we are applying some live load, dead load acting on the member. Say, for example, there is a load acting on it. So you go on increase the load. So somewhere, it is going to develop the cracks, okay, in the member. Right. Likewise, treating this as a bonded pre-stressed member, so that I am drawing the regular cracking pattern. Okay. So once the load is reached a certain level, the bending moment WL square by 8 reach certain value. At that bending moment, when you start seeing the cracks at the soffit of the beam, okay, so that is the moment where the visible cracks appear. That moment is called cracking moment. Okay, once the member cracks, then the behavior of the member is going to be similar to the RCC. Okay, so that is what is the importance of cracking moment. Okay, so cracked sections are to be dealt similar to RCC. Okay, right. After transfer of pre-stress to concrete from steel, the soffit of the beam will be under compression. That is the initial stage. After tensioning the tendons, once you cut the or remove the jacking, the tendon is going to come back to its original position, but the concrete whatever is having surrounding around that tendon will not allow it, because concrete has gripped that member, the tendon. So while the tendon is coming back to its original position, concrete will be under compression. That will make the member to hug, bend in the upward direction. That is what is called bottom compression. Okay. Gradually, these compressive stresses are balanced by the tensile stresses due to transverse loads on the beam. So when the pre-stressing stage is over, we will take the member to the structure, and we will place in the structure. Then it starts taking the load, its self weight, live load, all that. Okay. So in that case, the member is going to bend in the sagging manner. So then the bottom tensile stresses tries to develop. So already there is bottom compression is available because of pre-stress, and bottom tension is from the loads. So these are going to balance each other. So that is what is a mechanism. Uh, Primarily what we are being talking about, the advantage of pre-stressing. Then further increase in loads, if you go on increase the loads, because compressive stresses are constant values. Once you induce some compression value, and that will never change. Okay, the tensile stresses will change according to the load that you apply onto that member. So you go on load it. If you increase the load, the tensile stresses at the bottom are going to increase. So if the tensile stresses are very less, the bottom compression will be there. If the tensile stresses are exactly equal to compression, then bottom stress will be zero. Then if the load is still increased, then the tensile stresses cross the compressive stresses, and that will lead to the cracks. Okay. Right. Further increase in loading develops tensile stresses at the soffit of the beam. Okay. So a concrete is weak in tension, that everybody knows is a fundamental property of the concrete. So micro cracks develop when tensile stresses exceed 80 to 100 into 10 power minus 6 micro cracks, in the sense you can't see them. So if the tensile stress is somewhere 80 to 100 megapascal into 10 power minus 6, even for a very minute value of tension, the concrete cannot take even a very small tensile force, I mean tensile stress. So it develops micro cracks, which no will be only seen under microscope, right? Then if the loads are further increased, then visible cracks appear and the cracks will come onto the surface. Okay. It starts from the crack width, where whenever you are looking at a crack means minimum to see a crack, the width has to be 0.01 to 0.02 mm. Okay. So that is visible crack range. If you are looking at a concrete member, if you are able to see a crack means the crack width should be minimum should be 0.01 to 0.02 mm. So beyond that, the crack width is going to be increased to 5 mm, 10 mm, something like that. Okay. Right. In general, visible cracks appear if the tensile stresses at the bottom are approximately equal to modulus of rupture of the material, means the possible tensile strength capacity of the material, if that is crossed. Okay. So that, 0.7 root FCK is your the IS 456, whatever it says, the tensile strength of concrete, okay, is the uh, 0.7 root FCK value, right? So if that value is crossed, then we will have visible cracks appear. That is what is the information regarding what is a cracking moment, how the crack is going to propagate, all that. Okay. Let us see an example how this cracking moment is going to affect the different parameters. A rectangular concrete beam of cross section 120 by 300. So let us draw a cross section of 120 mm by 300 mm. Is pre-stressed by a straight cable carrying an effective force of 180 kilonewton at an eccentricity of 50 mm. So 50 mm is the eccentricity. This is being the center of the section in CG. So first 50 meters, it will be 150 from here to here. So the three parts, if you three equal parts we can make, this is the first 50. So 50 mm is the gap between this. So 50 mm is the eccentricity value. The beam supports an imposed load of 3.14 kilonewton per meter uh, Q value over a span of 6 meters. So beam is having 6 meter span. Okay, with a live load 3.14. If the modulus of rupture of concrete is 5 Newton per mm square, mean FCR, you can use the symbol, or else let us see what Krishna Raju used. Evaluate the load factor against cracking, assuming the self weight of concrete as, gamma of concrete as 24 kilonewton per meter cube. Okay. Load factor. Load factor. What is meant by a load factor? Okay. So, load factor means what? Okay, it is like load factor means uh, bending moment, bending moment required for uh, developing cracks. Okay, that means cracking moment. Okay, and actual bending moment. Working bending moment. Okay, so bending moment required for developing cracks at the bottom. Okay, that value divided by what exactly is the bending moment acting uh, under the service loads, that is working loads. So MW that we call. So this ratio is load factor. Okay. So if you increase the service loads and make this working bending moment is equal to cracking moment, then cracks starts appearing. Okay, so that is what is called load factor. It is the ratio of cracking moment to working moment. Okay, so your job is now to find the working moment and then cracking moment. Okay, right. So because the stress at cracking is given to develop cracks, how much stress is required is given. So 5 Newton per mm square tensile stress should be there at bottom to start developing cracks. So find M cracking, then take the ratio of M cracking with MW, that will give you the load factor. Okay. So let us see what are all parameters we have. Load pre-stressing force given 180 kilonewton, eccentricity given 50 mm, cross sectional area you are able to find it out 120 into 300, and moment of inertia you are able to solve bhq by 12, 120 into 300 cube divided by 12, z bh square by 6, you are able to solve it, and dead load value cross section in terms of meters 0.1 to 0.3 into gamma 24, that is giving you 0.86 kilonewton per meter. So live load is already there, q is 3.14 kilonewton per meter. Okay, right. So total load now 0.86, 3.14 is giving you 4 kilonewton per meter is the total load. Now stresses due to pre-stress is P by A. Okay, what is P? 180 divided by area 36 into 10 cube, that you do. So 180 kilonewtons, that means 180 into 10 cube newtons divided by cross sectional area is like 36 into 10 cube. So this will give you 5 megapascal is the stress due to pre-stress, which is direct stress. Now PE by Z, stress due to bending uh, due to pre-stress, bending stress due to pre-stress, P into E by Z. P 180 into 10 cube, E 50 divided by Z, you substitute whatever is available here, 18 into 10 power 5. Okay, so that is what is this one. So that is 5 Newton per mm square. Okay, Next, stresses due to loads. Total load is taken as 4, calculated as 4. So WL square by 8, because it is simply supported beam. So WL square divided by 8 is actually written as 0.125. Okay. So that is giving you 18 kilonewton meter. So M by Z, stress due to loads, M by Z is 18 into 10 power 6 by 18 into 10 power 5. So this is 10 Newton per mm square. Now, what we want is stress at bottom. Okay, what is stress at bottom is 0, because 5 P by A, this is P by A, stress at bottom, plus PE by Z minus M by Z. Okay, so this is due to pre-stress and this is due to loads. So 5 plus 5 minus 10 is 0, right? But the stress corresponding to cracking at the bottom means, when you want to see cracks at the bottom, what should be the value? 5 Newton per mm square. It is given here. So 5 Newton per mm square. If it is not given, you have to estimate like 0.7 root FCK. Okay, right? So if the FCK, you have to assume and get it. Right. So to have cracking at bottom, you need to have 5 Newton per mm square stress. So that is no extra. It is actually 0 for the present load value. For the present load of 4 kilonewton per meter, 0 is the bottom stress. So if you increase this load, okay, then this 0 will become 1, 2, 3, likewise. So to have 5, okay, what should be the bending moment, right? So that is what is now required. So extra moment required to create this stress 5, okay, that is M by Z. What I want is 5, okay. So M by Z value, I shall have 15 here. Instead of 10, we shall have 15. Then this will become 5. Okay, 15 minus 10 will become 5, right? So 5 is required value. So 5 into Z is equal to bending moment. 5 into Z is 18 into 10 power 5. So that is giving you 9 kilonewton meter is the additional moment required. Okay, 18 is not sufficient to develop 5 stress at bottom. 18 kilonewton meter is developing 0 stress at bottom. So increase this moment, okay, by what value? Plus 9. If you increase it 18 plus 9, then it is going to develop a moment value of 5 Newton per mm square. Okay, so this is what is called cracking moment. Okay, so cracking moment is 27 divided by working moment is, for the present load of 4, what is moment? 18. Okay, so 18 is the working moment. So the load factor is 1.5. Okay, so load factor denotes the moment required for developing the crack. Okay, so that is what is the ratio of cracking moment to working moment is the load factor value against cracking. Okay, so this is the example that which clearly explains you about the cracking moment. Okay, right. So this is about the unit 2 of your syllabus. So I will be posting the assignment questions for this unit. So do practice the problems in this unit 2, where the analysis of pre-stress is being done elaborately. So it almost took 27 sessions to complete it, around 27, 28 sessions. So we will move to the unit 3 in the next session onwards, loss of pre-stress. We will be talking about. So we will be inducing pre-stress by jerking the tendons. Say if you induce, say if you are reading maybe digital or analog form, if it is showing, say for example, 1000 megapascal is induced in the tendon, but it will not be 1000 throughout the life of the member. Okay, so that is what we are going to talk about. What factors will influence the loss of pre-stress, and how much is the loss? Say if 1000 is induced when the member is manufactured, I mean, after transfer stage, after service stage, maybe after 1 year, after 2 years, after 10 years, after 50 years, okay, what will be the pre-stress available in the concrete member? That is important, because concrete pre-stressed concrete member is going to deal with high amount of stresses. It is always no, required to be taken care at every stage. Otherwise, it is going to give you lot of problems when regard to pre-stressed concrete members, right? Okay, thank you. Next session, we'll talk about loss of pre-stress.